All right, well, welcome to Lecture 2 for CSE 215, Discrete Structures. So we're going to continue from where we left off last time. We were talking about set operations and identities, and I said that we were going to go on from there to something called a membership table. And a membership table is a way that we can think about how sets interact with one another. And the idea is pretty simple. Suppose we have two sets A and B. And imagine that we pick any element in the universe. Remember, we've always got a universe set, right? Which is the set of things from which elements can come from. So think of any element in the universe. And we can ask the following question: is that element a member of A? And we know it either is or it isn't. So if it's not an element of A, we're going to write a 0. And if it is an element of A, we're going to write a 1. So 0 means not an element of A. 1 means it is an element of A. And we can do the same thing for B. If this particular element we're thinking of is not a member of B, we can write a 0. But if it is a member of B, we could write a 1. And so we have 4 possibilities. It could belong to neither A nor B. It could belong to B alone. It could belong to only A, or it could belong to both. One of those 4 has to be true, and exactly one of those 4 will be true for any element we think of. Well, we can do some things with this. For example, if we know whether an element belongs to set A and set B, we can say, does it belong to the union? And if our element does not belong to A or B, it does not belong to the union. But if it belongs to B, if it belongs to A, if it belongs to both, it will absolutely be in the union. We can think of the intersection, which requires that an element belongs to both A and B. So in this case, the element belongs to A and B. It'll also be in the intersection. But in these other cases, for example here, it belongs to B, but it does not belong to A. It's not part of the intersection. And if we think about the complement, which is the set of things that are not in A, well, if we're thinking of an element that's not in A, it will be in the complement. And if we're thinking of something that is in A, it's not in the complement, because the complement is the set of things that are not in A. So we can write these membership tables, and they should look familiar to you. This is an OR function, this is an AND function, this is a NOT function. So they look very similar to things that we did in Engineering CSE 250. And we can use them in a similar way. For example, let's prove the following identity. Let's prove that A union B intersect A is the same thing as A. Well, I've got all combinations of A and B, and I know what A intersect B is the same as B intersect A. And so let's just go ahead and say what's A union B intersect A. So I'm looking at this column, and I'm looking at this column, and I want to take their union. Well, something belongs to the union if it's in one set or the other. So these first 2 rows, not in either set. But here it's in A, and here it's in both A and that intersection. So it's in both of those. Now, if I look at this column and I look at this column, I can observe that they are exactly the same value in all cases. This means that for any element that I think of in the universe, either it is not a member of either set, or it's a member of both sets. And when we talked about equality of sets, we said 2 sets are equal if every element is either in both or in neither. Well, that's the situation we have here. Any element is either in both of these sets or it's in neither. That's enough to say this set must be equal to that set. So we can use membership tables the way we use truth tables. In 250 we use them to prove identities about Boolean variables, and here we can use them to prove identities about sets and set operations. So that's the deal with membership tables. Alright, another thing that will be useful is sometimes talking about families or collections of sets. For example, I can define a set A equals something, B equals something, C equals something, and so on. But I could also define a family of sets, for example a set A subscript I, and I could say this contains the elements 0, 1, 2, 3, up to and including I. And I might define this only for I bigger than or equal to 0. So I've got a whole collection of sets here. I've got A1, which is the set 0, 1. I've got A0, which is the singleton 0. I've got A5, which is a set containing 0, 1, 2, 3, 4, 5, and so on. So I can define collections of sets, and we can do some of these set operations over these collections using an idea from algebra. For example, suppose I wanted to do A2 union A3 union A4 union A5. I could write that as the union from I equals 2 to 5 of A subscript I. So it's just an abbreviation. And we can do the same thing with an intersection. So you'll have some homework problems to play around with this, but this is similar to that summation notation that we're going to talk about in a few minutes, but that you've probably seen before. Alright, so another thing that's useful to know about sets is that we can represent sets in a computer very easily if we adopt a convention on the elements from which we can build our sets. So remember, a set is not ordered, right? 1, 2, 3 is the same set as 3, 2, 1. But if we impose an order for the sake of this representation, we can come up with an easy way to represent and work with sets in a computer. So let's suppose that our universe consists of a series of integers. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So any set in our universe is some collection of these 10 elements. Okay, I'm going to impose an order which will be exactly, this order that I've written them in. And I'm going to have 10 spots, one for each element. And so if I have a set, let S1 be the set containing, 3, 5, 7. I'm going to represent that as a binary string as follows. It does not contain a 0, a 1, or a 2. It does contain a 3, no 4, 5, no 6, 7, no 8, or no 9. This would be the string corresponding to S1. And if I wrote S1 as, 7, 5, 3, I get exactly the same string, right? I'm not saying that these sets are suddenly ordered. When I write down this string of 1s and 0s, I'm using a particular ordering of the elements. That's all. So S1 might be the set 3, 5, 7. There's the string. Let S2 be the set 1, 2, 3, 4, 5. So that would be no 0, 1, 2, 3, 4, 5, no 6, 7, 8, or 9. Okay, this binary representation is really useful for computer representation of sets, because here's what we can do. If I wanted to do a union, I can just do a logical OR of these two strings. For example, if I OR these, I get 0, 0, 1, 0, 1, 1, 1, 1, 1, 0. If I AND these strings, I get a 0, 0, 0, 1, 0, 1, 0, 0, 0, 0. And if I negate, for example, S2, I get 1, 0, 0, 0, 0, 0, 1, 1, 1, 1. Okay, so just doing Boolean operations on these representations. If I go back to my computer representation, what does this set represent? It's the set containing 1, 2, 3, 4, 5, and 7. This is the set containing 3 and 5. And this is the set containing 0, 6, 7, 8, 9. Well, guess what? If I take the union of these two sets, I should get 1, 2, 3, 4, 5, 7. That's what I got here. If I take the intersection of these two sets, I should just get the 3 and the 5. That's what I got here. And if I were to take the complement of this, I would get 0, 6, 7, 8, 9. That's what I got here. So there's two advantages to this. One, it's a way to represent sets as a string of binary numbers, which works well for computers. But two, it lets us do set operations by doing Boolean operations on these strings of 1s and 0s. If I do an OR between two Boolean strings, that gives me the union of the corresponding sets. If I do an AND, it gives me the intersection. If I do a negation, it gives me the complement. So we have a way to go back between sets and Boolean operations. And again, this idea that unions act like ORs and intersections act like ANDs, which is what we see in the membership table, which is what we saw looking at set identities. This is a theme that's going to keep coming up again and again. All right, next topic, functions. So what is a function? Function is a mapping from one set to another. So take two sets, A and B. We can say F colon A to B. This is a mapping from A to B. Meaning for each little a in the set A, maps to some element little b in the set B. So pick any element from A, F gives you an element in B that corresponds to that. So it's a mapping or an assignment or a correspondence from elements in A to elements in B. And if you like pictures, we could think of it like this. Right? Each element here goes to an element over here. It's possible that two different elements here might go to the same element here. And it's possible that there's some elements here with nothing going to them. Those are all valid functions. The only time it's not a function is if this element went to more than one element over in B. That fails what we call the vertical line test. It's not a function, it's not well defined. One thing to note is that if we form a set whose elements are tuples, whose first element is A and whose second element is F of A, and this is the set of all these tuples such that little a comes from the set A, right? That is one way to define a function. And this is actually a subset of just the Cartesian product of A with B. Alright, so how do we specify functions? Well, we can write an equation, for example, f of a equals a squared. We could make a table, f of 1 equals 1, f of 2 equals 4, f of 3 equals 9. Or we could write this set of tuples. We could say 1, 1, 2, 4, 3, 9, and we could make a set of all these tuples, and if we want to know what f of 2 was, we just find a tuple with 2 in the first position. Second position is f of 2. We could define this in words. We could say f carries a to the square of a. So there's different ways we can define functions, but we can always come back and think of it as just a mapping of elements here over to elements there. Alright, some terminology. If f goes from a set A to a set B, set A is called the domain. Set B is called the codomain. And the set of all values that are actually mapped from something in A, this is called the range. So these are just pieces of terminology. So for example, maybe I have f going from the integers to the integers, defined by f of x equals x squared. So the domain is z, the set of all integers. The codomain is z, the set of all integers. But the range would be the set of all things that are mapped to from something. So it would be the set of integers 0, 1, 4, 9, 16, 25, and so on. So the range will be some kind of subset of the codomain. In this case, we also could say f maps A to B. Right, so we can use the word map and function somewhat interchangeably. F is a map from A to B. The function f maps the set A to the set B. The range is also called the image of f. If you think of f as kind of projecting things from A into B, the range is the set of things that get projected from A. So it's the image. And then there's things we can say about the nature of a function f. So f colon A to B can be surjective, or sometimes we use the term onto, which means every element of B is mapped from something in A. So f is surjective if everything over here has something going to it. If every element of B has an arrow going to it, that's surjective or onto. That also means that the range is the same thing as the codomain, right? Everything in B gets mapped to from somewhere. This can be injective, or sometimes one-to-one, which means if A1 is different from A2, then f of A1 is different from f of A2. So an injective function does not do this. It does not have two different points going to the same thing. If different things in A always go to different things in B, that's injective, or one-to-one. And finally, a function could be bijective, also called one-to-one onto, if it's both surjective and bijective. So a one-to-one onto or bijective function has both properties. Different points here go to different points there, and every point over here in B has something going to it. And bijective functions are really nice because they establish what we can think of as a one-to-one correspondence between points here and points there. So bijective function gives us a one-to-one correspondence. Everything in A maps to everything in B, but each thing in A can be associated with one and only one and exactly one thing in B, and vice versa. So that's a bijective map, and those are very important. We'll come up to those later on when we talk about the size of sets. What else is there to know about functions? Two functions are equal if they give you the same value at all points. That's kind of obvious. All right, moving on, let's talk about sequences and summations, and then we'll wrap up with just a little bit about matrices. So what is a sequence? It's an ordered collection of things. So for example, it could be 1, 2, 3, 4, 5, 6, 7. That's an infinite sequence. It could just be 1, 2, 3. That's a finite sequence. It could be 1, 2, 1, 2, 1, 2, 1, 2. That's an infinite sequence. It could be 1, 2, 1, 1, 2, 2, 1, 1, 1, 2, 2, 2. That's another infinite sequence. It's just an ordering of things. And it could be finite or it could be infinite. It can definitely have repeats. It could have a very simple pattern that's easy to describe. It could have a pattern that's very hard to describe mathematically. It could be a random sequence that we don't have a way to describe. It could be taken from the decay of radioactive particles and measuring how long it takes from one decay to the next. And as far as we know, there is no formula that describes the sequence you would get. It's a truly random occurrence as far as our science understands. But it's still a sequence. All right, so we can write this sequence, and we can reuse some notation. We'll reuse notation a fair amount in here. We use curly brackets for sets, but we can also use it to describe a sequence. And so I can say curly bracket AN to represent the sequence A1, A2, A3, A4, and so on. And so for example, if I was describing this sequence, A1 equals 1, A2 equals 2, A3 equals 1, A4 equals 1, A5 equals 2, A6 equals 2, A7 equals 1, and so on. And this is not a set. It's a different use of the curly brackets to represent something very different. So that's a sequence. But there are sequences we can define using formulas. For example, I could define the sequence AN equals n squared. And this would be the sequence 1, 4, 9, 16, 25, and so on. I shouldn't put brackets there. The sequence AN would be this set of numbers 1, 4, 9, 16, 25, and so on. All right, and we can think of sequences as functions. So this might describe a function from the natural numbers to some codomain. all these sequences I've been defining seem to come from the integers, so I could think of these as like functions going from perhaps the natural numbers to the set of integers. And for this sequence up here, f of 0 equals 1, f of 1 equals 4, f of 2 equals 9, f of 3 equals 16, and my general formula might be f of n equals n plus 1 squared. I could define a sequence as a map from the natural numbers to the reals, and my formula might be f of x equals 1 over x plus 1. So f of 0 equals 1, f of 1 is a half, f of 2 is a third, f of 3 is a quarter, and so on. And so my sequence would be 1, a half, a third, a quarter, a fifth, a sixth, and so on. And this is like a discrete version of the mathematical function y equals 1 over x, or 1 over x plus 1. And it's not the same thing as this curve for y equals 1 over x. It's a set of points here and here and here and here and here, right? So discretization, discrete structures, right? So sequence, just a collection of elements from some set, and we can define that collection, which is ordered, right, by thinking of it as a function from, say, the set of positive integers or the natural numbers to that particular set. We can also think of these things as strings, right? If we had a sequence of letters, or if we had a sequence of zeros and ones, we could think of that as a string, a bit string. And so if we have some binary number like this, we could also see that as a sequence of 8 bits. So it might be a map from the set 0 through 7 into the set 0, 1. I will say more about strings towards the end of the course. Alright, why are sequences interesting? Because they let us talk about something called a recurrence relation. And recurrence relations are critical to everything we're going to do. So a recurrence relation, this lets us describe a sequence of things a sub n with an expression, or maybe multiple expressions, a sub n equals some combination of a1, a2, up through a n minus 1. Okay, let's unpack this. A recurrence relation is a way to describe a sequence by describing each term as some combination of the prior terms. Okay, recurrence relation is an expression that lets us define the nth term as some combination of the first n minus 1 terms. For example, I could say a subscript n equals a n minus 1 plus 1. So the nth term of my sequence is just the previous term plus 1 more. Alright, so you may have an initial condition. For example, I might say a1 equals 1. Well, if I know that an is an minus 1 plus 1, and I know that a1 is 1, I know the entire sequence. Right? Since a1 is 1, this relation up here tells me a2 is equal to a1 plus 1. And I know a1 is 1, so this is 1 plus 1. So a2 is equal to 2. And a3, according to this relationship, is equal to a2 plus 1. And I just found a2 is equal to 2, so this is equal to 2 plus 1, which is 3. And so my sequence corresponding to this would be 1, 2, 3, 4, 5, dot, dot, dot. And we call this a solution for this recurrence relation. Alright, so let's just do some examples of this. I think they'll make more sense than trying to formalize those definition further. So for example, a subscript n might be n times a n minus 1, and a1 is equal to 1. Well, what does this look like? And when you're trying to analyze a relation like this, sometimes it's easier to just sort of work through a few examples. So here's our recurrence relation. Let's just start off. a1 equals 1. a2 is going to be 2 times a1, so it's 2 times 1, which is 2. a3 is going to be 3 times a2, which is 3 times 2, which is 6. a4 is going to be 4 times a3, which is 4 times a3 is 6, which is 24. So the first few terms of our sequence are 1, 2, 6, 24. Now maybe you recognize that, maybe you don't. If you don't recognize it, one thing that can be useful, instead of just plugging in values like this, is to do a bit of an expansion on these terms. So let's look at a5. This relationship tells us it's 5 times a4, and a4 is 4 times a3, and a3 is 3 times a2, and a2 is 2 times a1, and a1 we know is equal to 1. So if this is 2 times a1, this is 2 times 1. So a2 is 2 times 1, which means a3 is 3 times a2 is 2 times 1. a4 is 4 times a3, and a3 is 3 times 2 times 1. And a5 is 5 times a4, which is 5 times a4 is 4 times 3 times 2 times 1. And now it's a little clearer what's going on. a5 is 5 times 4 times 3 times 2 times 1. So the nth term of the sequence would seem to be the product of the first n integers. And we have a way to write that mathematically, which is just a subscript n. The nth term is just n factorial. We'll deal with factorials a lot around week 7 of this course when we start talking about probability and such. Relatively simple idea, just a mapping from sequential integers to some set. That's a sequence, but we can sometimes find this recurrence relation, which describes the nth term in some combination of the prior terms. In this case, this describes factorials. Here's another recurrence relation. an equals 2 times an minus 1, a1 equals 2. And if we expand this out, a1 equals 2, a2 equals 2 times 2, which is 4. a3 will be 2 times a2, which is 2 times 4, which is 8. and so on. And if we think about this, we can deduce that an is just 2 to the n. And so our sequence would be 2, 4, 8, 16, 32, and so on. So that's a geometric sequence. And sequences come up in lots of situations. So, for example, interest. So you give your money to a bank, and they're supposed to give you money back in addition to what you gave them for the use of your money. That's called interest. So let's suppose that you get 5% annual interest. So at the end of each year, they give you 5% back on whatever money you loaned them. So the amount of money you loan them, that's called the principal. So we'll write P1 is, let's say, $1,000. So that's the initial amount of money that you give them. After a year, P2, you would still have that initial amount plus a little bit of interest, 5% of that $1,000. So that's 1,000 plus 50, so you get 1,050. The next year, you have your 1,050 that you started with, plus you get 0.05 back on the amount that you had in the beginning of the year. So how do you figure out how much money you have after 40 years, other than doing this 40 times? Well, if we think about this, your principal at year n plus 1 will be your principal at year n plus your principal at year n times 0.05. That's what you started with in the beginning of the year. That's what the bank gave you at the end of the year as interest, 5%. We can factor out the Pn, and we find that each year your new principal is just your old principal times 1.05. So let's rewrite this. P1 equals 1,000. P2 equals 1,000 times 1.05. The next year, you would have this amount multiplied by 1.05. So you get 1,000 times 1.05 squared. Your fourth year, you would have this amount multiplied by 1.05, which is 1,000 times 1.05 cubed. So after 40 years, you would have 1,000 times 1.05 raised to the 40th. So what is 1.05 raised to the 40th? It's 7.04. So you would have a little over $7,000. So after 40 years, you've got 7 times as much money as you started with. So that's how investment works. So that's a real world example of a recurrence relation. And we have this recurrence property. Pn plus 1 is Pn times, whatever the multiplicative factor is based on the interest rate. And we have an initial condition. What P1 is, that's the starting principal. All right, let's talk a little about summations. summation is just this funny sigma symbol. You've encountered these before, right? Typically we say something like the sum from I equals 1 to 5 a subscript I. And this is just a shorthand for the following. Same letter A, nothing to do with sequences that we were talking about a minute ago. A subscript I is just some collection of values. This symbol is just a shorthand for this expression. Right? That's all it is. So for example, suppose that AI is equal to I squared. So we could say, what's the sum from I equals 3 to 6 of AI? Well, that's just a shorthand for A3 plus A4 plus A5 plus A6. And if we know these values, this is 3 squared plus 4 squared plus 5 squared plus 6 squared, which is 9 plus 16 plus 25 plus 36, which is 25, 50, 86. That's all there is to it. But there's some interesting properties on these summations. For example, the sum from I equals 3 to 6 of AI is also the same thing as the sum from I equals 1 to 4 of AI plus 2. So if I is 1, this will be A3. If I is 4, this will be A6. So it's adding up the elements from A3 through 6, same as this. Alright, so what is this? This is like a for loop. We could say for I equals 1, I less than or equal to 5, I plus plus. Sum equals sum plus AI. Maybe that's, an array, a element I. So initialize your sum to 0, and then this is just doing a running sum inside a for loop. This could be something like, sum equals 0. For I equals 3, I less than or equal to 6, I plus plus. Sum equals sum plus I times I. So I times I is element A subscript I, and we're just adding all of those up inside a for loop. So this would be the sum from I equals 3 to 6. This would be a for loop I equals 1 to 4, but everywhere that we use I inside here, we use I plus 2 over here. This is also the sum from j equals 3 to 6 of aj. That's just, for j equals 0 or j equals 3 instead of I. Doesn't matter what we call the variable, right? Same thing here. It doesn't matter what the variable is. It's almost kind of like a placeholder of some sort. Sometimes we might see the sum over j bigger than or equal to 3, less than or equal to 6. So you might see that notation. Or you could see the sum over I contained in the set 3, 4, 5, 6. So there's different ways to represent the same notation. I could say sum over all the elements I of this set. So 3, 4, 5, 6. Same as that, same as that, same as that. And then there's some properties that we should know. For example, if I do the sum from I equals 1 to 10 of AI, and I add the sum from I equals 1 to 10 of BI, that's the same as the sum from I equals 1 to 10 of the quantity AI plus BI. And why is that? Well, this thing on the left is A1 plus A2 all the way up to A10. this thing on the right is b1 plus b2 all the way up to b10. And I can rearrange these and write this as a1 plus b1 plus a2 plus b2 plus a3 plus b3 plus all the way up to a10 plus b10. And that's just the sum from I equals 1 to 10 of ai plus bi. So it's easy to demonstrate, at least for fixed cases like this, that we can bring these two things together into a single summation. And similarly, sum from I equals 1 to 10 of some fixed number k times ai is also k times the sum from I equals 1 to 10 of ai. In other words, we can pull this constant out. And we could demonstrate that by just taking this, writing out each of the terms, and then factoring out the k, and taking what's left and writing it like that. And if these look familiar to you from calculus, that's good, because we have these same kinds of rules when we do calculus, right? The integral of f of x plus g of x. Wow, I haven't written integrals in a while. The integral of f of x plus g of x dx is the same thing as the integral of f of x dx plus the integral of g of x dx. And the integral of some constant times f is just the constant times the integral. And why do these work? Because integrals are just summations. They happen to be, infinite summations, but we can do a sum from I equals 0 to infinity, and it means exactly the same thing, except we don't stop writing the things that we're adding together. So I can do the sum from I equals 0 to infinity of 2 to the minus I, and that's going to be 1 plus a half plus a quarter plus an eighth plus a 16th, and we're going to keep adding these things together. And if we were to do this forever, we would end up with something closer and closer to 2. If we do it forever, we say we end up with 2. So now we're talking about limits and convergence of sequences and all the stuff that we don't want to do. But it's all connected, right? So all the stuff you did in Math 151, 152 is still relevant. But we don't need to remember any of that. All right, last piece on summations is we can do double summations. And so you may see cases where we've got a summation that includes a summation as one of the things we're adding. So for example, you might see the sum from I equals 1 to 3 of the sum from j equals 2 to 4 of I times j. Okay, if you want to figure out what this is equal to, break it into pieces. First, just think of this piece. And what is this thing in brackets? Well, set j equal to 2, this is I times 2. Set j equal to 3, this is I times 3. Set j equal to 4, this is I times 4. This is the same as that, right? All I did was write this down with j equal to 2, 3, and 4 and add them together. And so this whole thing on the left is just the sum from I equals 1 to 3 of this. And now I can do the same thing again. Set I equal to 1. This is 1 times 2 plus 1 times 3 plus 1 times 4. And then if I is equal to 2, this is 2 times 2 plus 2 times 3 plus 2 times 4. And then if I is equal to 3, this is 3 times 2 plus 3 times 3 plus 3 times 4. It's monotonous, but it's straightforward. Although a better tactic might have been to combine this and said, oh, 2i plus 3i plus 4i, that's 9i. And then I could say this summation is just 9 plus 18 plus 27. And that's a little easier to do. But that should be what you get if you do all of this. So double summations, just do the inner summation first. Treat it like just, you know, an expression by itself. It will have extra variables in it, that's okay. And then just do the summation of that. And if I had another summation outside, I can do that too. No problem. All right, so that's summations. The last thing I'll mention on that, there's also this uppercase P symbol, product. We can say product from I equals A to B, f of I. And it's just like a summation, but we multiply instead of adding. So this would be f of A times f of A plus 1 times f of A plus 2 all the way up to f of B. So just like summation, but instead of adding, we multiply. All right, last topic is matrices. And if you've taken, or if you're taking Math 215, linear algebra, you learn all about matrices. We're not going to go deep into matrices here. I just want to mention them because they'll come up one or two times very sort of superficially. What is a matrix? It's a big set of square brackets with some numbers inside. That's a matrix. What does it mean? That's a bigger question. But this is a 2 by 2 matrix. And this is 2 rows and 2 columns. So those are rows and those are columns. And we can do different things with matrices. For example, we can add matrices. So 1, 2, 4, negative 6 plus 1, 0, 2, 0. And to add two matrices, just add element by element. 1 plus 1 is 2, 2 plus 0 is 2, 4 plus 2 is 6, negative 6 plus 0 is negative 6. There's our addition. We can subtract exactly the same way, and we can multiply by numbers by just multiplying element by element. So if I want to take this matrix and multiply it by 10, I get 10, 20, 40, negative 60. We can transpose a matrix. So if I take 1, 2, 4, negative 6, and I transpose it, it just means swap the rows and columns. So my first row is 1, 2, that becomes my first column. My second row is 4, negative 6, that becomes my second column. And if M is the same thing as its transpose, then we say M is symmetric. So for example, that's a symmetric matrix. Because if I transpose it, this first row 147 will become the column, which is 147. The second row 423 will become this column 423, and the third row 736 would become the third column 736. We would get the same matrix. So that's a symmetric matrix. There's a matrix called the identity, which has 1 on the diagonal and zeros everywhere else. And that's a symmetric matrix. And you know, these were 2 by 2 matrices, these are 3 by 3 matrices. You could have a 4 by 4, you could have a 2 by 4, you could have a 1 by 8 matrix. There's no restrictions on the dimensions, as long as the dimension's bigger than or equal to 1. Alright, the other thing we can do is we can multiply matrices. And multiplication of matrices is not a straightforward process. We don't just multiply each element here by each element there. We do something much more complex. But it turns out to be a useful operation to perform. So let's look at multiplication. We're not going to really use this the rest of the course, but you probably encountered this. You might have encountered this in 120. You'll definitely encounter it in Math 215. But let's just touch on it in here and see how multiplication works. All right. So here's multiplication of matrices, and I'll show you a specific example, and you can generalize it if you like. But I just want to kind of show you there is a way to multiply these things. So let me stick with 2 by 2 matrices. So let's do 1, 2, 3, 4, and let's multiply by 2, 0, 3, 5. I'm just making these up. Okay, so the product is going to be a 2 by 2 matrix. And to find the thing in the first row, first column, we take the first row here and the first column here, and we do what's called a dot product. And we say 1, 2, and we dot it with 2, 3. And that gives us 1 times 2 plus 2 times 3. So we take the first things, multiply them, take the second things, multiply them, add them together. So this is 2 plus 6, which is 8. That's the thing that goes up here. To find the thing in the upper right corner, and let me do it up here, we'll take the first row and we'll dot it with the second column, which is 1 times 0 plus 2 times 5, which is just 10. So there's a 10 up here. So we could be using our summation ideas here, right? If these elements are AI and these elements are BI, it's the sum of AI, BI for I equals 1 to 2. Alright, second row, first column, take the second row and dot it with the first column. That's 3 times 2 is 6. 4 times 3 is 12. This is 18. And then second row, second column, take the second row and dot it with the second column. 3 times 0 is 0. 4 times 5 is 20. That's 20. So our product matrix is 8, 10, 18, 20. Which is not super obvious from just looking at these two matrices. So that's the procedure for multiplication. So one thing to note, that identity matrix I, if we multiply A times I, we always get back A. And if we take I times A, we also get A. Multiplication is not commutative. If I do this times that, then my first element upper left would be this dotted with that. It would be 2, 3 dotted with 1, 2. 2 times 1 is 2. Oh, we got the same thing. I did it backwards. If I did this times that, I would take my first row, 2, 0, dotted with my first column, 1, 3. 2 times 1 is 2, 0 times 3 is 0. This would end up being a 2. So in general, A times B is not going to be the same thing as B times A. And sometimes A times B isn't even something that makes sense, depending on the dimensions of A and B. So if we had a 2 by 5 matrix, we could multiply it by a 5 by 6 matrix. That would be fine. but a 5 by 6 can't be multiplied by a 2 by 5. Math 215, you find out all this stuff. But the last thing I want to mention about this, and this is why matrices are so important, this is why you do an entire course in linear algebra as a computer science student. The whole reason is the following. We can define equations like this: a times x equals b. And with matrices, with algebra, we can define a single relationship: a times something equals b. We want to find out what that unknown something is. With matrices, we can define a series of 2 or 10 or 100 or 1,000,000 equations, all with a single matrix equation. And to solve it means to solve 1,000,000 equations simultaneously and find a solution that makes all 1,000,000 of those true at the same time. That's a powerful thing to do, right? That's what drives kind of the engine of our modern world, is the ability to describe a system as a series of equations and then find a solution for it. This is how people buy and sell stocks. This is how people predict the behavior of complex systems. It's all matrix manipulation. So there's a great deal of interest in being able to solve equations like this. Well, if these were plain old, algebra equations like ax equals b, it's easy, just x equals b divided by a. But there's no division for matrices. There's no defined way to take a matrix and divide it by another matrix, except for one exception. So b divided by a is also b multiplied by the inverse of a. And in some cases, matrices have inverses. And so in this case, if I were to take a inverse times x equals a inverse times b, the inverse is the thing that when you multiply by itself, you get the identity element. So a inverse times a is equal to the identity. And the identity times x is just x. So if we know that matrix A times matrix X is equal to matrix B, we can find matrix X by taking A inverse and multiplying it by B. But finding the inverse of a matrix is a complex proposition. So the inverse is the thing that when you multiply by A, you get the identity. And there's lots of ways to find the inverse of a matrix, but they are very expensive in terms of computation. And they boil down to, guess what? The process of solving a series of simultaneous equations. And so you can do things like variable elimination, you can do determinants, you can do all kinds of things. They're all the same. And that's what Math 215 is, that's what linear algebra is. It's this connection between matrices and simultaneous equations and higher dimensional geometric spaces. All tied together, all different views of the same thing. That's Math 215. That's a separate course. But anyway, that's just a little bit of it. Like I say, we're not going to do anything with inverses and transposes and all that stuff. But we want the basic idea of a matrix. We're going to use the terminology later on when we talk about graphs and some graph theory. And you should, get a lot of this in Math 215, but this is either a quick refresher or a bit of a preamble. All right, that's it for lecture 2. Next lecture we will start talking about logic and Boolean logic and work our way up into proofs. All right, see you next time. Thanks.